All right, inhomogeneity corrections. So this is covered in Con Chapter 12, Section 12.5, and AAPM Report 85. And I have the report in the background, so if you need to go to it, I can flip to it. So let's get started. So you guys know already, heard of inhomogeneity corrections and what they're used for. You've seen it in treatment planning computers, right? In Eclipse, the AAA algorithm has a section where you can go in and turn it on and off, right? So you've seen that. In Exio, there's a section under the calculation menu that you pull down and you turn it on, and it gives you two options. And it gives you the option of doing heterogeneity calculations by pixel. You've seen that? Or the other option is by structure itself. And so you can do heterogeneity calculations either way. AAA also gives you that functionality to do it by structure, but it's handled a little bit differently. So anyway, why do we want to correct for heterogeneity? Pre-1970, when people were doing treatment planning, first of all, planning computers were not very sophisticated back then. The algorithms weren't sophisticated, and the ability to contour structures wasn't very sophisticated. We weren't using CT that often, it was mostly 2D. And so heterogeneity calculations were very difficult because of those two impediments. The calculation algorithms weren't there, and we didn't know what the structures looked like because we didn't have 3D. Once we started getting 3D, then we had more of a possibility to correct for heterogeneity, but then we were still limited by our algorithms. We were still limited by our algorithms in terms of the accuracy of the algorithms. And then we were also limited by the information of the heterogeneity. Because to get heterogeneity information, you need to know what's inside the structure, if it's bone or air. So we had some limitation on the accuracy of the composition. And so it took the United States, especially, a really long time to warm up to heterogeneity calculations for treatment planning. And then the other reason not to do it too were the question whether it makes a difference, whether it makes a clinical difference to include heterogeneity calculations in the treatment plan in terms of clinical results. No, it doesn't make a difference. So it took a really long time for this to come up. And then an argument that pushed heterogeneity was IMRT. Once we started doing IMRT, we started realizing that it's so important to get those dose gradients. Have you folks done IMRT yet? You've seen it? You know what it's about. It's about getting these dose gradients away from organs at risk, right? Pushing the dose away from organs at risk as much as possible through special algorithms. But once you're doing that, now you've got organs at risk, you've got your tumor close to each other, you're now able to push the isodoses away from the organ at risk. So to do that, if you're not calculating heterogeneity, you're not accounting for it. Now, you don't know if that gradient is in the right place anymore. Okay, so with IMRT, and with these extra requirements that we have with IMRT, we need to be a little more accurate, as accurate as we can be. Okay, and so then this was another argument to start using heterogeneity. So that's how heterogeneity kind of developed, and heterogeneity was espoused in Europe a lot before the United States started using it. Another reason that we didn't use heterogeneity for a long time is because the clinical data was all based on homogeneous calculations. For years and years, we were doing lung as if it was water, as if it had the same scattering. I mean, it sounds crazy to think about it today, but that's how we were doing it. Okay, and I talked to physicians about this, and they said, well, yeah, I mean, we've seen a lot of recurrence in lung patients come back for retreatment, and it's probably because we didn't really calculate the dose correctly back then. So patients aren't made entirely of water. We have to correct for it. Heterogeneity affects how much the primary beam is being attenuated, and mostly for points beyond the area of homogeneity, so inhomogeneity. And so if lung is your area of inhomogeneity, it's the points beyond the lung that get affected more, or feel the greatest effects. The electron fluence, or energy distribution of scattered electrons, are mostly for points near the area of inhomogeneity. So we need to be concerned about the electron fluence near the areas of inhomogeneity. And I'll show you some graphs that show the interface between a water medium and metal or bone, and how that interface is different when you consider inhomogeneity. And that's due to the electron fluence. So in megavoltage energies, from 0.05, which is 50 keV, to 10 MeV, in patient tissue, interactions are mostly governed by Compton effect. There's a really nice graph. Let me flip to it really quickly. There's a really nice graph in I'm sorry, in report 85. Oh, we're gonna have this problem again. Is this the quickest way to get rid of it? Oh, yeah, there's a really nice graph in here on the distribution of Compton effect and the probability of Compton effect. There it is. Here it is. So this graph shows you the fraction of interaction photons that undergo Compton scattering as a fraction of photon energy and the atomic number of the absorbing medium. So here's the photon energy, here's 1 MeV. What's our average energy that we treat our patients with?
Around 3.
Around 3, right? For 10 MeV, and maybe 2.5 or 2.2 for 6 MeV. That's the average energy. Okay, so we're not up here. Mostly we're down here. Okay, and so we're down here. And what's the Z for tissue?
7.
Around 7 something, right? Okay, so Z is up here, 10's here. So we're looking at something here. So look at here. These lines are probability lines or ratio lines of Compton effect as a fraction of photon energy. So Compton effect is almost 99 to 95% right around here, okay, at these energies. I'm sorry, at the Z. As Z gets higher, you start losing a little bit of Compton effect because there's some photoelectric effect going on too. Okay, all right. And then as energy gets higher, why do you lose Compton effect if you go this way? Yeah, you start gaining more pair production. Okay, so that's a nice graph that shows Compton effect. Doesn't it look like that graph that we saw back in the first quarter where we had 2 lines that went like this? Z was on the left and energy. It kind of looks like that. So that's what it's based on. Okay. Is that it? Yeah. So average about 80% Compton effect, which depends only on electron density. And electron density is electrons per cc. Okay. Can be electrons per gram, but we mostly use electrons per cc. In lower energies such as orthovoltage and superficial, 100 to 140 kV, the predominant problem, when I say problem, is the predominant material is that is affected by heterogeneity is bone, since the photoelectric effect is more prominent in bone at these energies, and that's due to what? High Z? What's the high Z material?
The calcium.
Okay. If the relative electron densities between water and other materials in the body are known, one can make attenuation corrections. Okay, so we've got a good thing going here. We know the Compton effect is 80% of the 80% of the interactions, and we know we can use this electron density information to calculate the Compton effect, the amount of Compton effect, so we can make corrections for that. So now this is a comparison of electron density, electrons per cc versus electrons per gram. And you'll see, you might see both of them, but it's important for us to realize which one we need to use. So, and this you can calculate based. You go to Johnson Cunningham or the back of Kahn, there's tables of materials, and at the top of the material, it'll tell you the electron. Can you flip over there one sec? Let's find out. I think they give you electrons per gram in the table. At the top of that, I think they're mass attenuation coefficient tables.
Yeah.
Okay, and at the top,
You give us electrons per kilogram.
yeah, electrons per mass. So electrons per kilogram, and if you go across and you look at the different materials, I have 3 outlined in this table. Electrons per gram, water, bone, and air. Look, they're pretty much the same. Okay, even air. Now, do you think that this is useful for attenuation? That air and bone are about the same electrons per gram? It's not that useful. We know that air doesn't attenuate just from just an intuitive feel. We know that air does not attenuate as much as bone. Okay, so this is not a very useful measure. But here's what we use. We use electrons per cc for corrections, and this is in units of 10 to the 23rd electrons per cubic centimeter in water, bone, and air. So bone has more. Okay, it's just to go from here to here is just a matter of applying the mass density of the material. Okay, so electrons per gram. Electrons per gram times the mass over volume. Yeah, so we multiply the density times this, and you get this. Okay, so these two are pretty close, and air is a lot smaller because of the smaller density, lower density. So for planning purposes, we need to know the number of electrons that are in the linear path of the photon beam, not how many there are in one gram of material. So as you're calculating the attenuation of one photon, say, you need to know how many electrons this photon is going to hit to calculate the probability of this photon interacting. Okay. The electron density is typically given as a ratio of electron densities to water. So when we say electron density, we mean electrons per cc, but sometimes we need electrons per cc of material divided by electrons per cc of water. Okay. Electrons, and so that's sometimes it's not clear in the books. So you'll see electron density, and it'll say like 0.98, but that's obviously not this number here. It's the ratio of that material to water. Okay, so be careful with that. The electron density contains most of the information we need to correct for inhomogeneities, most of it. But again, electron density is what the Compton effect depends on, right? But we know there are other effects that happen. So the electron density is not the whole story. Okay? So a large increase in C, such as metal implants, may not be accurate due to the increasing proportion of photoelectric and pair production effects, meaning that the correction based solely on electron density and how it affects the Compton effect is not the whole picture. If you have a high Z, we don't have a way to correct for photoelectric effect or pair production in high Z materials. That's why when there's a patient with metal implants, and I'll talk about it at the end of the talk, if you just turn on your heterogeneity correction in AAA, you think that that's accurate, the dose in the metal is accurate, and beyond the metal, it's not that accurate because of these two effects. Okay, so let's look at some examples on how we correct for this. So inhomogeneous material in the primary beam. This is a representation of a very nice oval patient. Photons coming down, and we have 4 points of interest that we're going to look at. And we have a dark lung, smoker, okay? Okay, so we have a point of interest above the lung. We have a point of interest inside, kind of near the interface, and one further down on the interface, and then one beyond the interface lung. And this is the density of water, and this is the density of lung. And we're going to look at how the heterogeneity affects those 4 points. And each of those points are considered to be a small mass of water equivalent material. Okay, so there's a little bit of scattering medium in that material. So as the photons traverse, point A will experience a slight decrease in dose due to reduced backscatter in the vicinity of lung. Okay, so now what I'm doing is comparing with lung versus no lung. Heterogeneity versus no heterogeneity correction. Okay, so if there is no heterogeneity correction, this was all considered water, point A would experience a certain amount of dose. Once we turn on heterogeneity and we look at the fact that there's air here, well, there's lung here, there's less backscatter because photons interact less with the lung. Okay. So the photons that would have interacted with water here are no longer interacting. So therefore, they're just moving straight down. And the probability of backscatter is a lot lower. So point A is going to be low. What happens to point B? Point B experiences more dose due to less attenuation in lung, but it experiences less scatter dose due to reduced side scatter in the low density material, that being lung. Both effects may possibly cancel. So what happens to point B? So point B now experiences a little more dose because there's less density here to attenuate the photons. So it experiences a little more, but there's less side scatter contributing to dose. So that side scatter meaning the stuff that happens on the sides of B. There's the stuff meaning the interactions that happen on the side of B are a lot lower. Therefore, B doesn't get any dose contribution that would have been there from side scatter. Okay, so in one sense it's higher because there's less attenuation above it, and then it's lower because there's less side scatter. Point C experiences more dose due to less attenuation in lung. Okay, so again, the photons get through, and the intensity of the beam here is higher at point C because there's less attenuation. This outweighs the fact that the lack of side scatter due to a large amount of low density above it. So point C will experience more dose than otherwise. Okay, then point D experiences more dose due to reduced attenuation than primary beam above it. That all makes sense, right? Pretty obvious. Now, one thing when we talk about the intensity of radiation, we can talk about it as in terms of fluence. Remember what fluence is? It's photons per could be cc or photons per area. Okay, or it could be dose intensity. It could be centigrade per minute. Okay. Now those would be really different if you look at, say, if you look at point C. If you look at point C, the fluence inside point C, photons per cc, is going to be pretty close to the fluence above it, inside and above it, because this is a tiny infinitesimal point, right? Photons per cc are going to be about the same. But what's going to be different in C versus lung is energy. It's going to be dose per minute, because C is absorbing a lot more dose than the photon, than the lung material above it, okay, because of the higher density. Okay. So when we talk about intensity, we have to keep those things separate, those two parameters separate. Correcting for inhomogeneous material. Okay, so this is one of the methods that we can correct mathematically for inhomogeneity. And this is the RTAR method. It's a pretty old method. I think some hand-calc computers still use this. Most treatment planning computers don't use this anymore. But anyway, it's a nice, simple example, and it'll give us a feeling of how to do the correction. So the inhomogeneity correction algorithms have been given different categories by Report 85. If you go into Report 85, there's categories 1 through 4, I believe, and they're all explained in there. Okay, so category 1 is the simplest, less sophisticated, and that means that local energy deposition, so that the energy is deposited locally, it's not going to consider electron transport. Electron transport is when an electron gets created and moves downstream and deposits its dose downstream, and the algorithm corrects for that. Okay, and it knows how far. Well, it knows how far most of them are. It's all probabilities, right? So it knows how far it is, and it corrects for any electrons that leave the local deposition. This is too simple for that. This does not correct for that. Okay, 1D sampling. That means that if the inhomogeneity changes on the slice below it or above it, if there's a different distribution, it's not going to know that either. So say there's only inhomogeneity on this slice, and the slice here and there are water equivalent. There's no lung there. Just assume some hypothetical case. It doesn't know that. This is a 1D sampling. It just looks at 1D. Of course, if the slice above it and if the slice is adjacent to it were all water equivalent, then this one slice might be negligible in terms of the dose because there's so much scatter happening next to it that it might wash out this inhomogeneity effect. That would be 3D sampling, where it takes into account the whole volume. But this is 1D. It only looks at the photons coming straight through. Simplest case. Okay, so, and this is how it works. So this is kind of cool. Determine the thickness of water that is equivalent to the inhomogeneous material. So we're going to use a method where we're going to calculate the equivalent depth. You guys use RadCalc? You guys use RadCalc in the clinic, yeah. You use it. And so you use RadCalc for inhomogeneity corrections. No, you haven't. Well, when you do an inhomogeneity correction in RadCalc, you have the option of picking equivalent depth, and that's what this does. Okay? I'm not sure if it uses RTAR or another method, but this is what it does. It calculates equivalent water equivalent depth. Okay, so for point C, the actual depth in this example is going to be 6 cm. The water equivalent depth is going to be less because there's lung tissue, there's less attenuation. So that's what we're going to do. So D prime is a water equivalent depth, and that's equal to D1, and D1 is the depth from the surface of an inhomogeneous material. So from the surface, being this surface, to the inhomogeneous material, to this material right there. That's D1. D2 is the depth from the start of inhomogeneous material to point of interest. So D2 is the value from here to point C, if C is our point of interest. Okay. And then rho medium and rho water, that's just the electrons per cc of medium, electrons per cc of water. Okay? Electrons per cc, not electrons per gram. Okay, so that's it. So you determine D prime. Then you use D prime to look up the TAR. Okay? And so you calculate the TAR for D prime. This is the correction factor that you can use. And it's equal to the TAR, D prime, for the field size that you're treating the patient with, divided by TAR of the actual physical depth of that field size. And then you apply that correction factor to the dose that you expect, and that's your corrected dose. Okay, so here, let's do an example. So in this example, I just rewrote the equations up here. Calculate the dose to point C from a 10 by 10 cobalt 60 beam. The depth at C is 6 cm. The depth to the lung is 2 cm. Depth to the lung being this depth right here, to the surface of the lung from the patient's surface. And then the ratio of electron densities in this case I'm giving is 0.33. Excuse me. This method overcorrects for density. This is just an aside. This method overcorrects for densities that are less than water, such as lung or air, and undercorrects for densities that are greater. So overcorrects for water, so overcorrects for lung, and undercorrects for densities greater, such as bone. Okay, so that's a disadvantage of this method. And then you can also use the ratio of TMR. Okay, so let's calculate that. So D prime is equal to 2. D1 was 2. Okay, plus 0.33. This is the ratio of the densities. And then the D2 is the distance from point C to the surface of the lung, and that's 6 minus 2. So then D prime is 3.3. Look up the TARs, get the ratio. Here's the correction factor. So we end up with a correction factor of about 10.8% higher dose for point C than if we were doing just water equivalent calculations. Okay. That's a very simple method of doing it. Here's another, and you can do. We typically don't do hand calculations of these things, but if you're doing, say you're doing a Klux plan, and you do a red calc, they don't agree. There's a heterogeneity calculation, and they don't agree. You need to have another independent way of doing it. So you can use these methods to calculate it, if the geometry is not too complicated. Okay, so here's another one. This is still a category 1, so it doesn't consider electron transport, and it's a 1D sampling. And this one is a little bit more accurate than the other one. And I would recommend this if you're going to do hand calcs. This one takes into account the distance from the interest point to the inhomogeneity. So this has improved accuracy for points near inhomogeneity, but still does not account for the shape of the structures. Okay, it's still 1D. What that means is it's still a 1D sampling. And if you use TMR instead of TAR, you'll get a 5% increase in improvement in accuracy. Okay. So here's the new correction factor. It looks pretty similar, except you don't have the D prime. You have these other depths called Z1 and Z2. Okay, and then you've got these are, by the way, these are to the power of this. Okay, to the power of rho 1 minus rho 2. So rho 1 is the density ratio, remember the ratio, density ratio of the point of interest material. Okay, in this case, rho 1 is going to be a density ratio of C, and which is what? Whatever that was numerically. 0.33. So rho 1 is going to be 0.33. And Z1 is the distance from the point of interest to the interior surface of that material. Okay, that's going to be this distance. Rho 2 is density ratio of the next or overlying material. So this, you can actually use this to calculate materials of different densities. So you can have water, you can have bone, you can have air there. And I think Kahn has an example where he's got 3 densities. Okay, so in our case, what's rho 2 going to be? Just 1, correct. Okay, so Z2 is the distance from the point of interest to the interior surface of the material with density rho 2. So Z2 is, so Z2 is going to be this distance from the point of interest to the interior surface of rho 2. Okay, so let's do the example. Calculate the dose to point C from a 10 by 10 cobalt 60. These values are still the same. Okay, so Z1 is the distance to the interior surface. It's 4 cm. Z2, so that's the distance from the point of interest to the top of the anterior surface of the lung. Z2 is the distance from the interior surface to the, from the distance to the interior surface of the other density being water. And that's 6 cm. We look up the TARs for, this is the Z1, okay, 0.94, and that's TAR of Z2. That's 0.867. The correction factor is 0.94 to the power of rho water medium minus, what was that equation? Rho 1 minus rho 2. Rho 1 was 0.33, rho 2 was 1. And then this one's going to be 1 minus rho 2, and rho 2 is 1. Okay, so this becomes to the power of 1, so this becomes 1 on the denominator. And so the correction factor is 1.04. See the difference? There's a huge difference between our chart and the back though. One was 10%, the other was 4%. This one's a little bit more accurate. Okay. So effects on isodoses. How does this affect isodoses? And once you start doing some planning, it's hard to understand if you're doing multiple beams what's going on with the heterogeneity on versus off. So we're going to look at a single beam. This comes from report 85. And this is a beam of photon. Not sure what the energy is. Doesn't say. No, it doesn't say. But anyway, here's a non-homogeneity. And then we're going to introduce a section here of lung. Okay, and let's look at this. Let's kind of pick it apart and see what's going on here. As the photons interact, when the photons interacted in water, they deposited most of their energy locally, and so did the electrons. Because remember the PEVs of electrons? They'll travel a certain distance and they drop really quickly. Okay, so they don't penetrate that much. When there's a heterogeneity involved, those electrons are now able to travel a lot further. So any interactions that occur in the lung material with photons are going to set electrons in motion. Those electrons will now no longer interact as readily as is the case with water. So since they don't interact as readily, they're now able to straggle their way outside of the radiation beam and deposit their energy out here. Well, what happens if they deposit their energy outside of the radiation beam? The energy inside this beam is diminished. There's less energy here because you lost that energy. It's going somewhere else. You can't create energy. There's only a certain amount of energy. So what happens is these isodoses tend to pinch in. They come inside because your dose inside that area is reduced. So the isodoses come in. So these isodoses that would have otherwise covered the tumor, and now the dose is a lot lower in this area, the absorbed dose. Okay, but some of the photons that go straight through are depositing more energy downstream. So the dose being absorbed down here is going to be higher. Okay. So that's what happens. You lose energy to the sides, and what you're trying to treat, if it's inside the lung, is getting less dose. And here's an example. I'm going to hit the lights. I can see this. So this is I think this was a breast patient, and I just put an APPA beam on a breast patient with implant. Don't worry about the implant. So this case here is no homogeneity correction. In that case on the right is with homogeneity correction. And let's look and see what happens here. With right at the edge of the lung, look at it. There's a kind of a disconnect here that's happening. So the photons that would have deposited their energy down here, see, look at this isodose line right now. That isodose line has moved inwards. Okay, so if you trace this blue one, for example, this is like way over here now. Okay, and so where is this energy going? This energy that would have gone here is now leaving the radiation field and it's going outwards. And you see how they bow around the lung, and they don't bow around the lung in this case. Okay, so for many years we were treating a lung tumor. Imagine a lung tumor that's in here. It looks like that. So for many years, say we want to cover this lung with the blue line. Okay, the blue line could be the 95%, and we thought that we were covering the lung tumor with that 95% because the tumor. So I'm going to try this same tumor here. Okay, in this case, well, 95 doesn't really cover it. Say the green line. The green line could be the 90%. And we were covering with the 90%, but look at what we were actually covering it with. Okay, so there could have been cases that this part of the tumor here recurred because it just didn't get enough dose. Okay, so that's the disadvantage of not using heterogeneity calculations. Okay. And typically when you're using an APPA beam like this, you'll have, with heterogeneity calculations, you'll have more dose here and here. What does that say, 123.4? I can't see the numbers. But anyway, you'll tend to have a little bit more dose at Dmax because there's more penetration through the patient. Now, this is obvious when you look at an APPA beam. But once you start using multiple beams, it kind of washes out a little bit. You don't see that effect as not as great. And then the other thing that affects this too is when we're looking at this, and This is, let's see, is this AAA? Yeah, this is AAA. The algorithms will also be different between AAA, between when you guys use an Axio, the superposition. The isodose lines will be different. So you'll do heterogeneity calculation of AAA, and you'll do heterogeneity with superposition, and they'll look different too. So that's another difference that you need to take into account. You also have to understand that there's other algorithms besides that. You might hear a pencil beam algorithm. So that one's even inferior to AAA. The accuracy goes kind of like, of the main ones that we use out there, pencil beam is the, well, I'll even go back one step. Clarkson, have you heard of Clarkson?
Yes, the book.
Yeah, that's right. Clarkson, I don't know if I'm spelling this right. Clarkson integration, that's the least accurate. Then there's pencil beam, okay. Then there's AAA, well, and then there's convolution. Maybe you know what, I'm going to do one thing. I'm going to flip convolution and AAA. It's convolution on its own. Convolution. And then there's AAA. And then there's superposition. These are the kind of the increasing accuracy. Oh, and then there's Monte Carlo. And I'll talk about these a little bit more later on another slide. Monte Carlo is another one. Monte Carlo. Okay, so this is increasing from least to most. Now, the I-plan, and how does this affect us clinically? I'll give you an example. With the I-plan treatment planning software from BrainLab that we use for radiosurgery, that's mainly designed for brain, for treating brain, doing treatment planning on brain. But we also use it for treating stereotactic body radiotherapy, which means a very short course of radiotherapy for lung or for spinal lesions. For short course meaning 5 fractions. Okay, very high dose per fraction. So we started using iPlan for lungs. Now, with iPlan, we only had this option, pencil beam. That's the only algorithm we have. Now today, you could spend a lot of money and get this option on iPlan, Monte Carlo. Okay. But we were using pencil beam for a while. And so then we started, as we did that, I went to talks, and people were saying that pencil beam is terrible with heterogeneity corrections. And they showed examples of pencil beam algorithm versus Monte Carlo or superposition. Huge difference. And so I went back to the clinic right away. This was a while back when we started using it. And then I started comparing it to our Eclipse and AAA, and I saw the differences too. Now, the differences were not, we were doing, just to roll back a little bit, in terms of the treatment planning for stereotactic body, we were doing arcs. We were doing a big arc here and a big arc underneath. So if we compared a large arc or multiple arcs between pencil beam and AAA and Eclipse, the differences weren't that great. But if we were looking at short arcs, possibly because there was something in the way, we didn't want to hit a kidney or we didn't want to hit too much lung, so we had to shorten the arcs and the beams were more narrow. That's when we started seeing the differences. And so in those cases, once we saw that, we said, forget it, we have to commission. We have to do all of our SBRTs on Eclipse. And so we dropped iPlan for stereotactic body and went to Eclipse because the difference was so big. That's just to give you a clinical example of how these algorithms may affect you in the clinic. So then it's AAA. It's still not, we don't have superposition for Eclipse. It doesn't exist. There's a new one that Eclipse or Variant is selling, and that's called the, what do they call, Accuros. Accuros. This is a new algorithm, and they claim that it's as accurate as Monte Carlo, but it's a lot quicker. Okay, so this is a variant product right here. Monte Carlo is pretty generic. Different planning companies offer Monte Carlo. Superposition is also pretty generic. AAA is a variant product. Oops. Okay.
So is there a reason that everyone just doesn't use Monte Carlo?
Yeah, money. It's expensive. Money is number one. It's expensive. It's pretty new. Number two is speed. Monte Carlo takes a really long time to calculate. I mean, right now, whenever we do a AAA plan, if it's a simple 3D plan, it takes a minute, 30 seconds to calculate. To do a rapid arc plan in AAA, it could take 20 minutes. So we're already bogged down with time. We don't want to, if we go to Monte Carlo, we're going to even be more bogged down. Unless, I don't know, Accuro supposedly is pretty quick. So I don't know much about it. Okay? All right, so let's look at some more theoretical stuff here. This is a graph of 80 keV photons. These are the questions that you might see on the boards, by the way. They like to throw this stuff at you because it's a little confusing. So, so here's a graph of 80 keV photons, the PDD, percentage depth dose. And what they've done is they've included this thick line is the PDD without any heterogeneity materials, and then the dotted line is considering bone. And this part right here of the graph is just soft tissue. Okay. And then here, this is where the bone ends, and then it goes on to soft tissue again. So let's look at what happens as photons penetrate at low energies and they hit bone. So at low energies, there's an increased absorption in bone due to high Z. Okay, so think 80 keV, and don't think of megavoltage energies right now, due to high Z and photoelectric effects. So at the energies of bone, all of a sudden, you're going to start absorbing a lot more material, and then drop as you get through. Why does it drop? So attenuation. It drops through the bone, and then once it hits soft tissue again, the amount of absorption is going to drop because the density is lower. But look at this difference. Why do you think this difference is here? Well, the reason it drops is because of attenuation. But why is there a difference between water and between a homogeneous material and an inhomogeneous material past the bone?
Because the beam is attenuated by the high Z material.
Yeah, right. So the density, so the intensity
drops.
Yeah, because a large chunk of that, what would you say, intensity has gone away. Okay, it's been absorbed by the bone. So that energy has to go somewhere. Again, the energy it's been deposited somewhere, so it's no longer present here. So it can't be this high because we've lost all this energy inside the bone. Right? And where does that energy go, by the way? Where does that energy? We say the bone absorbs more. Where do you think it goes? That energy.
To electrons?
Yeah, it goes to electrons, right? So those electrons. Then where do those electrons go?
Scatter all out.
Yeah, well, they scatter outside. If they're on the edges of the bone, they'll scatter out. And then they're also, if they're inside the middle of the bone, they can't get out because the Z is so high. So they just interact inside and create a lot more damage. There's a lot more energy deposited locally inside the bone. So that's where the energy goes. Okay. So now, let's just a hypothetical situation. What would the percent ionization curve look like? So this is the PDD, but what if you've got a chamber, hypothetical chamber that can scan through bone? Okay, so you're doing a PDD, you've got a water tank, and you've got a hunk of bone in the water tank, but this chamber is able to go through the bone. Okay, what would that percent ionization curve look like? Would it look like that? We know what it looks like in water. It just looks like a PDD. Percent ionization looks very similar to PDD with photons. What would it look like if it's able to go through bone? Well, this part would all be the same. So it would go like this. But what happens when it hits the bone? It's going through the bone.
Then there's more ionization in the bone, right?
Yeah, there's more ionization in the bone.
So when it looks similar.
Well, think about what this is. This is the bone absorbing, the bone itself, the bone material absorbing the electrons and the energy. But the chamber itself is made of, there's air in the chamber. So the air is not absorbing the same amount of electrons and energy as the bone is. Okay, so you'd see something like this. You'd see some kind of drop like this, because think about if you're a chamber and you're going through bone, you're experiencing a decrease in intensity because there's more attenuation. Okay. So that's just a hypothetical case. The question that might come up on the board. What would an ionization chamber experience? Or another question is, what's the fluence? What's the photons per cc? That's another question. It's not going to be this. It can't be higher. The more photons per cc. There's only a limited number of photons. It's got to be lower because there's more attenuation. Okay. So that's the distinction. Again, the distinction between absorbed dose and fluence. Okay. All right. So then, So then let's go down here. So the dose to the bone is equal to dose to water times the ratio of mass attenuation coefficients. So that's where this curve comes from. This dotted curve comes from this equation here. Dose of water times mu. We remember what mu n over rho is. Mu n over rho is the absorption. It's how much is being absorbed, and that's the ratio between bone and water. So let's open Con and let's calculate what this ratio is for 100 keV photons, just as an exercise. Then you have the Con available there. The table. So what table would we look at? We need to go to the table that indicates the mass attenuation coefficients.
For bone?
Yeah.
For mu n over rho for 100 keV. 3.39 times 10 to the second.
3.39 times 10 to the second. What are the units? Probably meters squared per kilogram. That should be at the top of the table, no?
There's a 0 and electrons per kilogram. So it doesn't give me oh, in meters squared per kilogram, that would be 420 energy.
And multiply by, I think it's going to put like 10 to convert. We usually, a more common unit is centimeters squared per gram. Con gives it to us in meters squared per kilogram, and they probably do this to, I don't know, have less numbers, or I don't know why they do it. But anyway, I guess just to stay consistent with the densities. So anyway, so these numbers multiplied by 10 to convert to centimeters squared per gram. So let's do that. So it's 3.39 times 10 to the 3 centimeters squared per gram.
Since we're going to divide one by the other, the units will fall out anyway, if we get them from the same table.
Yeah, I know. I'm just being complete. Yeah, you're right.
Actually, that's for 100 UV, not 100 kV.
Oh, okay. Oh, yeah, watch out for that. You can't erase that number, it won't let me. Okay, so just into the 3 centimeters squared per gram, just to get an idea of the numbers. So that's mu absorbed over rho for bone.
So that's for 100 EV.
Oh, yeah.
It's 2.959 times 10 to the negative third.
2.959 times 10 to the what?
Negative third.
Negative third. Now, did you multiply that by 10?
No.
Okay.
So 10 to the negative second.
Okay. That's a big difference between 100 EV and 100 keV. We're talking about a factor of 5. Okay. Okay, and then what about water?
3.1 times 10 to the negative second centimeters squared per gram.
Okay. So let's divide them. What's the ratio? Somebody do a calculation. So bone over this. It's going to be close, but 955. Okay. So this tells us that the dose to bone is equal to the dose to water times 0.95. So the dose to bone is around 95% of what the dose to water is. Okay, for 100 kV. Was that mu n over rho, or was that mu over rho?
That was mu n over rho.
Okay, 100 kV might be too high. As the energy gets lower, this number is going to get bigger than 1 because of photoelectric effect at some point. Let's do 50 kV. So bone.
3.159 times 10 to the negative second. And 3.159 0.299 times 10 to the negative second.
And these are both, you multiply by 10, right?
Yes.
Okay. So,
You're
boom.
still getting
They're still a little bit lower. They're still a little bit lower. I guess the energy needs to go even lower. Remember, because F med. Oh no, F med is air. That's right. But bone, as you go, that's
30 kV is where.
Yeah, we got to go even lower.
That's the first point where you'll get a number greater than.
Yeah.
Oh yeah, I lied.
So this is 50. This is 100.
Yeah.
What's 30?
30 is 2.994 times 10 to the negative 2
Is this bone?
for bone.
Yeah.
And 2.966 times 10 to the negative 2.
So this is water. So that's when it starts getting. That's where the bone starts getting higher. And then as you go even lower, it's going to get even higher. And that's because of photoelectric effect. Okay. And that, if you remember back to the F med graph, and F med it looked something like this. This was bone, went down like that, and then there's this air is a straight line, and water and muscle were something like this. They crossed over. So down here, this I suspect is down. This is less than 30 kV down here, when bone is higher. Okay. But F med, remember F med is bone to air. Okay, so there's a little bit of a difference there because water is below air. Below? Is it below or above? I can't remember F med now. It might go like this. It might go like this. I can't remember. Okay. A little exercise there. All right, what about high energy heterogeneity? So for high energy, at higher energy, the dose absorbed by bone is lower than that in soft tissue due to the fact that the ratio of mass energy attenuation coefficient is lower. See the F med. Let me just go back one second here. You know, at 80 keV, we should have gotten a big difference here at 80. Between UN over rho, bone water. Because look at the ratio between this and this. So that's MEV. So let's look at 80 keV. That's 8 keV. There's 80 keV. So let's look at 80 keV and here. For water, I'm getting, for 80 keV, I'm getting 2.58 E minus 3. See, there's a big difference there. Okay. It's, I don't know if those numbers are all.
Yeah, I'm off by a factor of 10 on all.
Okay.
Yeah, I see it on mine.
This seemed a little bit funny to me.
It's like twice as
Sorry.
big.
Okay. No, that's okay. Here, let's just.
No, I was off by a factor of 10.
Yeah. So let's just
It's
erase.
one of those years. It's one of those years.
But this is where, this is where you look at the numbers. You go, something doesn't look. This is where you go. Well, wait a minute now. If at 30 kV they're almost the same, how is it that at 80 kV there's such a big difference? So that's where,
Yeah.
And then those graphs, I know those tables are hard to read because there's so many numbers. You almost have to like put a straight edge there to make sure you're picking the right number off of there. And the units, they have like e to the 4, e to the 6, so, and it's all in EV, it's not KV, so it's something else you need to think about. So yeah, I mean, if you use the right numbers, you're going to get that curve correct. High energy heterogeneity, these are the kind of numbers we were just calculating, okay, where they're a lot more similar.
Right.
Okay, so at high energy, the dose absorbed by bone is lower than in soft tissue due to the fact that the mass energy attenuation coefficient is lower. And then here I say to see the F med graph for that. Okay, And then this graph just shows how that the energy absorbed in a dose is a little lower than that of water in a cobalt 60B. Okay, you know what? Let's stop here. Let's just take a quick break. Get a drink of water or something. Okay, moving on. Okay, so dose effects in soft tissue due to bone. So what does bone do? When bone's in the way, what does it do with a soft tissue dose? So dose located upstream of bone experiences dose. Tissue located upstream of bone experiences dose enhancement due to electron backscattering. This effect decreases with increasing energy. Okay, so what does that mean? Tissue located upstream of bone. So the photons are coming in this way, and there's some bone here. The tissue, and here's the surface. The tissue upstream of the bone, so that's this area right around here, is going to have an enhanced effect. It's going to have an increased dose due to backscattering in the bone. And this effect decreases with increasing energy. So this backscattering effect will be lower for a higher energy than a lower energy. Okay. Dose to tissue located downstream of bone is energy dependent. So what happens to dose to tissue down on the other side of the bone? That's energy. Higher energies like 18 MV produce a higher dose at the interface due to electron fluence enhancement from pair production. Okay, so at 18 MV, now remember how pair production depends on energy, and at the higher energies, obviously it depends on energy because we know the threshold dose for pair production is
102.
Right. So we need higher energies to create to even start at that threshold energy. And so once we have photon beams of that high energy, and we also know that pair production depends on Z, right? Z squared, actually. So if we have a high Z material, then we've got more pair production occurring, and so therefore there's a higher dose rate at the interface due to the pair production enhancement in the bone. So this is the dose at the interface. This is the dose right here. So at higher energies, you're going to get a dose enhancement right there. At lower energies, such as 6 MV, we produce a reduced dose at the interface, then dose builds up initially with depth. Okay, so for 6 MV beams, and I have graphs of this. I have graphs of this with metal, but it's sort of analogous. So at 6 MV, the dose is lower at the interface, and then it builds up. There's a build-up curve that happens. So let's draw here's the bone, and let's draw the graph. So for 18 MV, so here's the PD. So for 18 MV, there's going to be some dose enhancement here. It's probably not a good graph. PD comes down like this, and there's going to be some dose enhancement at the edge of the bone. Okay, so the bone interface is here. The bone ends here. And then for 6 MV, the dose is going to look like this. It's going to increase up a little bit, and then it's going to drop down. And then for 18 MV, the dose is going to start high and decrease. Okay, so on the other side of the bone, for 6 MV, the blue line is a 6 MV. There's going to be a buildup effect, and this is a bit of an exaggeration. But for the 18 MV, it starts high due to the pair production. Okay, so the electrons are depositing dose right at the edge of the bone in the soft tissue, and then it decreases after that because the electrons get attenuated. So for parallel opposed beam, bone has a minimal effect for low megavoltage energies and has a small dose enhancement effect for higher energies. Again, so for a single beam, you see this effect is clear. Once you start having parallel opposed beams, things start to get washed out. Now, figure 1220. Let's look at figure 1220. Down you have your book out. So figure 1220 shows two beams This is a 6 MV PDD, and that depth. And these are parallel opposed beams. So for they have a what the so this is a beam coming in. Let's see. Yeah, a beam coming in this way, and a beam coming in this way. Okay, and then so this is for water. This is a homogeneous medium, and then for inhomogeneous medium, you get a distribution that looks like this. Okay, so 6 MV, and this is bone, by the way. This material here is bone. This is water. Water. Okay, so when there's bone, there's an enhanced. It drops a little bit due to attenuation down here, and then there's an enhancement of dose in the middle for 6 MV. Okay, and this is a 20 centimeter thick polystyrene film. Okay, I said water, but it's really polystyrene, sorry. Same idea, though. Okay, polystyrene phantom containing a bone substitute material. Doses are normalized to midpoint dose. So 100% is at the midpoint up here. Parallel opposed beam field size is 10 by 10. SSD is 100. Okay. So A is 6 MV photons, and then the 20. Then they have another graph of a 24 MV. 4 MV beam PDD and depth, and they have the first one is water, and water looks just so well. It looks like this, and then bone. Dose perturbation perturbation plus attenuation. Okay. And then the bone looks something like this. So there's a much bigger effect at the high energies in bone. For parallel opposed beams. Okay, so those are effects in bone. Now, what about lung? And bone doesn't concern us all that much because remember the electron per cc difference between bone and water is around 5 to 3. Bone to water is 5 to 3 electrons per cc. And air to water was like 0.005 to 3. Okay, so we're more concerned about lung inhomogeneities and low-Z and low-density materials than we are of bone. So lower lung density means higher dose to the lung at deeper depths due to reduced attenuation of the photon beam. Laterally scattered electrons will contribute to dose outside of the tumor field. We saw that already. The periphery of the tumor, so this is the big disadvantage. Periphery of the tumor located in the lung will receive less dose than expected due to the loss of lateral scattered electrons. Okay, electrons will tend to scatter forward in low-Z materials, and low-density materials rather. The dose coverage effect is greatest for small fields at high energies. So if you try to treat a tumor in the lung with a small field, you'll see this effect. This would be a really big effect because a small field has less lateral scatter. So less possibility of lateral scatter. As you open up your field, you'll be able to cover more, but your isodose lines are still pinched in. So as you open up your field, remember the isodose lines do this. They get so for a certain field size, they look like this, and your field size may be out here or something like that. Those are your jaws. So as you open, and say your tumor is here, and you say, well, it's not covering my tumor. Well, what can you do? Well, all you can do is open up your field. So you got to make your field bigger. Your isodose lines are still going to, because there's heterogeneity, they're still going to get pinched in, but now you can cover your tumor. So to cover your tumor with heterogeneity corrections, you need a much bigger field size to get that scatter. Okay. But at some point, as you're opening your field size, you're treating above and below the tumor too. Or treating more because your field size is bigger all over. So you need to watch out for that. And in some cases, you just need to, you tell the doctor that this is the best you can do. He needs to increase his, possibly the dose that he gives the tumor, or the prescription dose, or the hotspot. So you can deliver. What you do is if you have a case like this, and this is he wants to give 180 a day to the center, for example, and this is 90%, but he wants to bring that 90% out, you can scale your monitor units up. Okay, so you're just scaling your plan up. So you're just increasing the MUs from AP, increasing the MUs for PA, okay, by scaling your plan. Now what you could do is you could tell the doctor, well, let's not prescribe to the center, let's prescribe to the periphery of the tumor. Or let's prescribe to here. Let's deliver 100% here. So now you're not delivering 100% here, you're delivering 100% here. So now you're covering your tumor with 100% isodose lines. But what happens when you do that? Your hotspot goes up. Everything goes up, right? Because we're talking about rescaling. So the prescription the doctor writes looks the same. 180 centigrade a day. 180 centigrade to what is the question. And depending on what point you choose for that 180, that'll determine your monitor units. Okay. So you don't have to tell the doc, okay, doc, you got to prescribe 250 a day because we're not covered. It doesn't need to do that. You could just pick a different prescription point. Because today, in the prescription, it doesn't say to the center, to the isocenter. It doesn't say to the periphery of the tumor. That's physician discretion. Okay. Of course, you also get to a limit. I mean, if you're prescribing 100% to the periphery of the tumor, now you're happy you're covering it, 180 a day to the whole tumor, you might be delivering 130% on your hotspot. And that's kind of high, 30%. So then, you reach limits. And 130, when I say 130, it sounds bad, but remember, we always have to talk about dose. So if he's delivering 180 a day here, and his hotspot's 130, what is that, approximately? What's that, 254?
No, 54 above.
54 above? Okay, so that's 230, that's 224, or 234. So it's 234 a day. The doc might say, well, 234 a day, the hotspot's in some area that's muscle, it's really resistant to radiation. I don't really care. I can do 234, but I really need to treat this tumor. Okay, so he might tolerate a really high hotspot. Anyway, that's the kind of discussion that you need to have with the doctor when you're doing treatment planning. And then also, don't give the doctor a plan that's got some insane hotspots. He's not gonna have much trust in you. So you need to understand from the back and forth discussions with the physicians when you're planning, you'll get a sense of what their tolerance levels are. And different docs have different tolerance levels for hotspots and for coverage. And when you're doing a plan, you might not know the background of this patient. This patient might have already had radiation before. So the doctor now wants to deliver a lot more. He wants to be more aggressive because he doesn't want to. This could be a retreatment. He wants to be more aggressive. You may not know that. So this is information that the doc would know that you don't know. So before starting a plan, it's always good to get as much background information as possible. Okay, so this dose coverage effect is greatest for small fields and high energies. Why is it greatest for high energies? Because high energies scatter more forward than they do to the sides, right? We know that there's more forward scatter. So if this is the tumor and they're scattering forward, well, here's the electron, it's going this way, it's not going this way. So there's a lot less side scatter, and therefore there's a lot less ability to cover that tumor. Okay, so this is a graph that comes from report 85, and this just is it's an overview of the calculation speed and of the type of heterogeneity correction that the different algorithms have. Today we talked about the RTAR and we talked about the batho. Those are the first two that we talked about. This one's a little more accurate than this one, if you recall. Calculation time is extremely fast. You see, calculation time is into the screen. Okay, it's this thickness in this direction. So these are really fast. Only considers primary photons, doesn't consider scattered photons, and doesn't consider electron transport, recoil electrons. Okay, here's another one, C-beam. I don't know if I've ever used this C-beam. I've never heard of it. This is even worse than these guys. It doesn't even cover primary photons. I don't know what it does. And then 2D, this is the irregular SAR, 2D fast Fourier transform technique, and this is the pencil beam. This is what we have with iPlan that I was talking about. So it looks like there's a little bit of thickness there, so the calculation time is a little slower than this one. But again, only primary photons, no scatter photons or electron transport. Okay, so these are not great for on the 2D FFT. This here is the that's the convolution algorithm. Okay, so that's not very accurate. You'll see convolution on Exio. Okay, so Exio has basically it has three main algorithms. It has the Clarkson, which is, it's not up here, I don't think. Clarkson. And then it has convolution, and then it has superposition. It has three main ones. And it has a fast superposition too. So it's a quicker version of superposition. And if you use convolution to do heterogeneity calculations, it's going to be very inaccurate. Okay, so I don't recommend. Convolution is great for homogeneous material, when you're not concerned about the pelvis, you're not concerned about heterogeneity. But if you want to do heterogeneity calculations with XEO, you need to use superposition or fast superposition. Convolution will give you very erroneous results. So moving down to 3D. So 3D means that it calculates the change in the shape of the structure as you move soup and into the patient, as you go through the different slices. It accounts for that. These are the 3D FFT is one of them. And this one again, oh, this is the one I'm talking about. 3D FFT, that's the XEO convolution. I would not use that. That's not accurate. It doesn't consider scattering photons or recall electrons. Okay, 3D FFT, but it does consider the three-dimensionality of the body, and the fact that the structures change from in the head to foot direction. DSAR, I'm not familiar with that. Don't know if any algorithm. I'm not familiar with trip planning systems that use that. So here's the superposition algorithm, and you see as soon as we get to superposition how the calculation time slows down. Wait, sorry. This superposition is. Superposition is this. So 3D FFT is this. So that's the calculation time for 3D FFT. Once you get over here, it starts getting a little slower. Superposition does take a little longer. And then Monte Carlo is the one that takes the longest, but it's the most accurate. And this is the only one that considers recall electrons. That's why it's so accurate. And once, I have another lecture, and I think it's the next lecture, where we talk about algorithms. And I'll get into the mathematics of the superposition algorithm and the convolution, and you'll see why that was more accurate from a mathematical standpoint. Okay, so when we talk about category 1, the RTAR and the batho, category 2 is local energy deposition. This slide should probably have been up higher. Sorry, it's out of order. Local energy deposition, no electron transport, 3D density sampling. So it does use the 3D data set, but it doesn't consider electron transport. And this is the ETAR method. I'm trying to think of what algorithm uses this. I think I've seen this. ETAR method.
I think they showed it on the previous slide.
No, I'm thinking the
See equivalent TAR 3D FFT.
Yeah, but I'm just trying to think of what planning system uses ETAR. I know that I've used one that uses it. I just can't recall.
Oh, you just wrote XEO.
Where? Oh, no. XEO.
See, it says ETAR 3D FFT.
Yeah, the ETAR. These aren't the same thing.
They aren't?
Mm-mm.
Oh.
No, they're different. This is one and this is another one. 3D FFT is the convolution algorithm. Yeah, I just circled the bottom one, not the top one.
Okay.
No, those are
the
different.
same thing.
No, they're different. Okay, so the ETAR method uses this. This is the correction factor for the ETAR. Again, it uses the ratio of TARs, and it uses the densities that are averaged over the path length from CT Hounsfield. So it uses the pixel by pixel calculation, and it averages the densities as the photon path goes through of the electron densities from the CT Hounsfield units. And the next slide will show how the CT Hounsfield units comes into play here. So ETAR and batho show dose inaccuracies of 20 to 80% compared to Monte Carlo. Okay, not too good, but that's all we had before we had Monte Carlo. Monte Carlo is considered the gold standard. But it's quite accurate in homogeneous non-water material. Homogeneous non-water material, like homogeneous lung, if the lung is pretty homogeneous and there isn't tissue and lung mixed in there. It's pretty homogeneous within lung, pretty homogeneous within bone if it's homogeneous. Longer calculation times compared to RTAR and batho. Okay, so how do we get, this is a graph that shows how we get electron densities, density information from our patient. We get it from the CT scan of the patient. Okay, and the CT scan comes from a scan that's done at 120 or 140 keV. Okay. And so from that energy, 120, 140 keV, we can get Hounsfield units from that. And then so the Hounsfield units are plotted on this graph here. And then the electron density ratio is plotted on the x-axis. Where does this come from? It comes from, I don't have a picture of this, It comes from a phantom that we call an electron density phantom. You guys might have seen it. It's typically circular or oval in shape, and it's about this big. It's like a typical thorax size of a patient. And there's plugs in it. There's a whole bunch of plugs in it. There's circular plugs, well, cylindrical plugs, that is.
Yeah, those are RSNA.
They did, that's right. Yeah, so you saw those phantoms, right? So these plugs, each plug has a different electron density. All right, so there's a plug for bone, and there's different bones. There's like cortical bone, soft bone. So there's different bone types, and we know the density. We know the electron density because it's stamped on the plug. There's plugs for water. There's plugs for there's one for titanium also, and there's polystyrene, Teflon. There's all kinds of plugs. What that does is it gives you a spectrum of electron densities that you know. Then you scan that in your CT scanner, and you apply. After you scan it, you apply a region of interest, and you calculate the mean CT number. Okay. So you calculate the mean CT number, you apply it here, and you get a curve that looks like this. So the treatment planning computer then, if you tell the computer to calculate based on CT numbers, it looks at each of the CT numbers in your patient and applies an electron density. So every pixel now has an electron density associated to it that it uses for heterogeneity calculations. Okay. So that's a little, it's okay, but it's not very accurate because, again, we don't have the photoelectric component, we don't have the pair production component. Okay. And we're also drawing electron density ratios from a scan that's a lower energy, a lower kV. And it would probably be this would probably be more accurate to get this information if we used a high energy scan, such as a tomotherapy CT scan. Okay, it would be more accurate. Because what is a CT number? It's mu water minus mu tissue divided by mu water, right, times 1,000. Oh, it's right there. Oh, this is opposite. So mu tissue. Sorry, I didn't know it was on the slide. The equation's right there. Now, these mu's come from, remember how mu is energy dependent? If we look at that table, as we go down, mu changes, right? These mu's that it's getting is for 140 keV. Okay, so we're getting CT numbers, we're getting mu's for 140 keV, but what we'd really like to get is mu's for our treatment energy. Okay, so that would be more accurate. That's what I'm saying. If you did this with the tomotherapy pen, you'd be a little closer. The electron density ratio would be a little more accurate because of this.
So can you do it with cone beam on the treatment table?
Well, cone beam is it's also 140 keV.
Oh.
Yeah, unless you use Siemens. Siemens has an MV cone beam, okay. And so you could do it with Siemens cone beam. So it'd be interesting to see how this would change with the tomotherapy unit. Actually, why don't you ask Brian Tom that? I wonder if he's done that. Make a note of that because they have a phantom. They call it the cheese phantom.
Yeah, I've seen that.
Yeah. So they use that cheese phantom. So ask them what the relative electron density ratio CT number is for. I don't know if he's done this, if he's looked at it, but it would be an interesting experiment to look at. This should be constant. The electron density ratio should be constant because it doesn't change. It doesn't change with energy. But what would change is this number right here, because we know that the mu's are different for different energy, right? So that would change. So question is the heterogeneity. So then, if you have this CT to ED graph from a tomotherapy high energy CT scan, then you'd have to use the high energy CT scan to plan for. You couldn't use a low energy CT scan and use a high energy graph because the CT numbers are different for the high energy and the low energy. So then the question is, if you plan up a high energy CT scan with this, is the heterogeneity correction more accurate? You get better results than a low energy CT to ED graph and a low energy plan. A low energy plan from a CT scan. So that's the question. Now, it would be difficult to plan, not difficult, it would be, it's a little more difficult to plan from a high energy CT scan because the high energy CT scan image is not as good quality as a low energy image. because of the higher energy, there's less contrast in a higher energy image. You know what I mean by higher energy CT scan? The tomotherapy unit has the ability to do a CT scan of the patient, but they use an energy that's, when they treat in tomotherapy, it's a 6 MeV. Okay, but they could detune that LINAC to bring it down to approximately 3 MeV beam. 3 MeV. So they detune it to get the CT scan. Okay, the lower they can get the energy, the higher quality the picture will be, because there's more photoelectric effect, which gives you more contrast. So, can you plan up a low contrast CT scan and then apply this? Or maybe what you could do is get a low energy CT scan and a high energy scan, fuse them, and use the high energy one to do the calculations, and use the low energy one to do the contours. Just anyway, Don, think of, if you remember those questions.
Yeah,
I think you're asking Brian about it.
I wrote it down.
Okay. See what, and that's your homework. Come back next time with the answer to that.
This could be a summer research project.
Yeah, it could be. Yeah, I mean, I think people have worked on it, but you can definitely expand on anything other people have worked on. If you guys want to do any research projects, if you have any ideas, now's the time to think about it. Because, well, first, the abstract, there's a couple of meetings you need to think about. There's the Midwest chapter meeting that is in April, around April 20th or so. And that meeting, we have a young investigator symposium. That's the first thing we do in the meeting. Typically we have 5, and I think I've told you guys before, we have about 5 talks. And so if you work on some research project, if you start now, you'll be able to have the data ready by April. And then I think the first prize is like $150 for that. And everybody gets some money, it just scales down. So that's one meeting you want to think about. That's the least pressure. That's a meeting of the least pressure because it's just local and it's nearby. And then the other meeting is there's a spring meeting, and I think that deadline is coming up like this week or next week. It's the 8 p.m. spring practical meeting. It's the first one of its kind. It's happening in May, and I believe it's in Dallas. And they also have a young investigator symposium. Okay, but I believe the deadline's like in a couple of weeks, so we don't have time for that. The other one that you want to think about is the annual meeting, 8 p.m. annual meeting, and that is in July, around the end of July somewhere. And that deadline, I believe, is in March. Okay. So that gives you time. Like I said, this is when you want to start thinking about a project if you want to present to either the Midwest chapter meeting or the annual meeting, the annual 8 p.m. meeting. Now is when you start, because this is where you start forming your ideas and start taking data. By the time the deadline to submit the abstract comes in, you've got something that you could submit. You can still work on it. Say you apply for a talk or a poster at the annual meeting, and you submit an abstract in March. You still have plenty of time to develop your data before you give your talk. So the abstract is an initial concept. You've got to have some realistic data that you trust, just to present the concept. But then you have more time from March, which is the deadline, to July, which is the meeting. You've got more time to think about it. So, but now is the time to pick a project and to pick an idea. I know you guys are busy with treatment planning and my homework, et cetera, but if you have some time, it's a good idea to start working on research at this point. It's good. It's a good experience. Okay, so CT inaccuracies. It's been shown that an uncertainty of 20 Hounsfield units in soft tissue can lead to an accuracy of 22%. All this data comes from report 85, by the way, all these bullets. So uncertainty of 20 Hounsfield units can lead to an accuracy of 2% in electron density. Uncertainty of 250 in bone can lead to 5% uncertainty in electron density. Since Hounsfield units give us electron density info, this only helps us account for Compton. I keep repeating this. It only helps us account for Compton scattering. It doesn't give us information about PET production or photoelectric effect. So this is these numbers are just give you an idea of if your CT scanner is inaccurate, if your CT numbers are inaccurate. This gives you an idea of what kind of inaccuracies you get in electron density correction. Okay. So this is an argument for doing CTQA. At least on a yearly basis, you should take a cheese pan, put it in a CT scanner, and scan your values to make sure they're consistent from year to year. CT scanners don't change that much, so you probably don't have to do it every week. Okay, once a year is plenty. What the therapists do in the morning is they do their own QA in the morning, and they do scan a water density. So they check the water number every morning. Okay, but there is a possibility that the CT scanner becomes nonlinear, meaning that if the water number is on, the higher CT numbers or lower CT numbers could be off. Okay. So that's what we should do once a year to avoid these inaccuracies. Category 3, so this is there's more accuracy, non-local energy deposition, electron transport. So this category 3 accounts for electron transport, 1D density sampling. So it just looks at it on a slice by slice. It ignores the slices above and below. So these are the convolution techniques. This is what EXA uses, or one of the algorithms that it uses. It uses a dose spread kernel, and we'll talk about this next class. It's multiplied and added to the terminal. Okay, and the kernel, just to give you an introduction to what this is, the kernel is, basically it's a matrix. It's a mathematical matrix, 3 by 3, 5 by 5, whatever. And it's a description of the probability that a photon is going to scatter in a particular direction. Okay, so in homogeneous mediums, the kernels typically look like this. If you plot the matrix, it looks like this. It kind of looks like a teardrop. Okay, so it's narrow down here and wide here, and so and what this means is that the probability of forward scatter is high. This is like a high energy, like an 18 MV kernel. The probability of forward scatter is very high. The probability of back scatter is low, and the probability of side scatter. So it gives you a probability distribution of where the photons are going to go. Okay, a 6 MV kernel is going to look more like this. Okay? It's going to be shorter. Okay, and it's going to be a little more rounded, something more like that. Okay, more back scatter, a little less forward scatter than 18 MV. Okay, so the distributions of where the photons are going to go. And then, so the kernel, and by the way, these kernels are calculated from Monte Carlo. That's the only way you can calculate these kernels, this energy, this angular distribution. So the kernel is multiplied to the term. The term has a total energy, the total energy deposited in the material.
It's released.
Released in the material, yeah. Okay, so, yeah, not deposited, released. And so the kernel and the term are multiplied and then they're convolved. And I'll show you the equations next class. And they're convolved, and we use a Fourier transform to perform that convolution, because it's a mathematical trick. And then we can use a fast Fourier transform to speed that up. We'll talk about that more next class. Then there's category 4, non-local energy deposition. So the electrons are transported out of the local site, 3D density sampling, so it's looking at the whole volume of the patient. And so this is where the superposition algorithm comes in. In the pinnacle world, it's called collapse cone. Okay, so I don't know if you've heard it in your clinic, it's called collapse cone within pinnacle. This method accounts for the distortion of the terma and kernels within the patient. So if this is lung, and this is tissue over here, and a photon interacts somewhere in the interface, the kernel no longer looks like that. The kernel may look like this. It may tip, because the probability of this photon scattering, or maybe in this case it would tip in the other direction. The kernel would tip in this direction because the probability of the photon scattering into lung is higher than in tissue at the interface. So this tipping of the kernels is something that doesn't happen in the convolution algorithm, but does happen in superposition, and that is it's a great improvement in dose calculation. Okay, so let's look at some of these graphs are from report 85, and so this is a good explanation. This is sort of the graphs that I was trying to draw with bone, okay, but we've got metal here. The same idea. It's a high Z material. So this first graph is 6 MV. So we have 6 MV homogeneous, which is this PDD right here, and then we have the squares are. This is like a titanium, not a titanium. It's a metal implant. It's a cobalt, chromium, molybdenum implant. That's what the implant is made of. Okay. And so the squares are broad beam and the triangles are narrow beam. So let's look at what happens for 6 MV. Look at the dose enhancement over here on this end of the upstream end. So there's some dose enhancement here, and then it drops really quickly. It drops a lot more quickly than here because it's metal. And the PDD drops up quickly, and then there's this build-up effect on the other side. Okay, so there's not much dose here, and then it builds up. And then what we're seeing here, we're seeing a split between the broad beam, this is broad beam, and the narrow beam. We're seeing a split down below. The reason there's a split is, just imagine photons going through a patient, interacts, and see some metal. We look at what happens on the other side of the metal. If a beam is really small, it looks like this. Okay? But now, if we open up our field size, what happens is that we have all this extra scatter that's scattering around to the sides and scattering on the sides of it, and it's scattering inwards behind the implant itself. So that scatter is adding to dose behind the implant. Okay? And so that's why the broad beam is higher. Okay? So the broad beam starts to approach the unattenuated PDB at deep energies. At deep depths. Okay, so that's 6 MV. So remember that 6 MV. Here's 18 MV. This one looks a little different. This part is similar. Okay, going back. Okay, it's similar up here. There's some backscatter. There's more backscatter here than 6 MV. But as you go beyond this implant, the 6 MV beam had this buildup effect here. This one doesn't have the buildup, and this is because there's an enhanced dose on the interface due to pair production. So all those electrons that are being created here create an enhanced dose here. Okay, and then that drops, and we see the same effect here for broad beam versus long beam, deeper depths. Okay, what about hips? So all those graphs really pertain to hips. So for hips, broad beam creates in scatter on the implant, which helps maintain PDD. Okay, we'll talk about that. Acetabular, what are the hips made of? So the acetabulum is, a hip is the hip part is the acetabulum, and then the ball interfaces with the acetabulum, and then there's the stem, which goes down into your femur. Okay, so there's an acetabular cup that's composed of polyethylene core supported by either this material or titanium alloy as the outer shell. The femoral component, and you should know this because when you're contouring, you might encounter prosthetic hips, and you'll have to contour them. Because contouring the prosthetic hip will allow you to assign electron density. It will allow you to assign whatever electron density you want to it. So you kind of have to know what these look like. So a femoral component is a stem and a head which can be hollow or solid. And it's made of the same materials and it could be made of steel as well. The physical density can be up to 17% different than the electron density. And the reason this is going to start becoming more important, these prosthetic hips, because of this. Aging population will show a greater percentage of patients with metal hips. So as we all get older, we'll start to see more cancer patients, and we'll start to see more hips because we're all getting older, and there'll be more older people out there with hips, metal hips. Recommendation: avoid beams directed through implants. So if you do see a patient like this in your clinic, try to avoid shooting through the implants. Now, what do we treat? We call this for prostate, gynecological, malignancies, rectum, bladder. Bladder's a little high, but it might still be in the way. So those are the main ones. So those are the sites that you'll see where implants might be a factor. It's very hard to avoid the implants if you're treating prostate because it's right in the middle there. Okay, but you could still do it. I mean, if the doctor wants to do a fork field, I would say, well, let's look at a fork field with obliques instead of two laterals and an APPA. Okay, so let's look at obliques and see what that looks like. Usually obliques, the thickness that you're going through, usually the distribution is such that you end up with little corners that go down into the rectum, so obliques are not, they usually give a little bit more rectal dose. So that's something to consider. But that's an option. Another option is also to use IMRT. Okay, with IMRT, you can contour the prosthetic hips and tell it not to give any dose to those hips. Okay, and you can orient your beams around it so that it avoids giving dose to the metal. Rapid arc is another solution too. Again, you're making those as structures that you don't want to give dose to, and so it avoids treating through. So there's some possibilities there. Another problem with these prosthetic hips is the CT scan artifacts. Okay, so there's metal on those hips, and so the photons don't get through the metal, so there's lack of information in the metal. So it's very difficult. So what was the consequence? Well, number one, it's hard to contour the prostate, bladder, and rectum. They're in this black area. And number two, it's difficult to do heterogeneity corrections if you want to do it because of all the streaks. Okay? But there are techniques, and I don't know if Theo's going to cover heterogeneity corrections in planning. Has he said that?
Not yet.
Okay. Well, just ask him about it. So there are techniques to get around that. or to mitigate that, I should say. So these are a couple of graphs that show you the effect of dose profiles on the downstream side of the metal hips. This one here is a 6 MV. Measured versus calculated height versus depths at different depths for 6 and 18. Okay, so this is a 6 MV beam, and they have measured and calculated values. I'm not sure how they calculated it. It's probably in the protocol. So the take-home message about this is that for 6 MV beams, there's a huge difference at shallow depths between the area. This is the area behind the hip. In other words, downstream. So there's a bigger difference at 10 cm versus 20 cm. Do you know why that would be? Here's the hip. Here's 10 cm and here's 20 cm. Okay, so the beam's coming this way, and this is the hip. Okay, and there's 10 cm depth and there's 20 cm depth, and this is a profile and this plotted in this direction. So why would the difference be greater between this point and this point versus a 20 cm depth between this point and this point?
Attenuation. You have more low energy. No. Difference. By the time you get down to 20, the side scatter kind of picks up.
There's more scatter. Yeah, I always tell people, if you answer scatter, you're going to be 50%. You're going to be right 50% of the time. But in this case, scatter is their answer. As you get further down, there's a lot more scatter occurring here. Well, there's more opportunity. There's scatter occurring here, 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 here. Those guys will all have the possibility of scattering behind the implant. Okay, so there's more opportunities for photons to interact down here and build up to the dose in the middle. Okay, and so for 18 MV, because there's more penetration through the implant, that difference is not as great. So if we look at this versus this, because the 18 MV photons are penetrating more, the difference isn't as great because there's more penetration. Okay. This effect, once you start adding a lot of beams, this effect kind of washes out a little bit, because if you have beams going through the implants like this, you can see the effect. But then, let's say you've got another beam coming in this way, and that kind of fills in the dose here. So this effect starts to disappear when you have more and more beams. Okay, but definitely something to consider, and I think we're done. Yeah. Yeah, ask Theo about you guys are going to cover heterogeneity and how. So, if we're treating prostate with these metal implants and there's streaks and artifacts all over the place, what I tend to do right away is I'll start a window and level my CT scan, so I just see the metal implants. Okay, and knowing what the metal implants looks like helps, because I know I'm expecting in the acetabulum I'm expecting this moon-shaped figure, and then I'm expecting a spherical figure, which is the femoral head, and then I'm expecting the stem. So you window and level until you have that shape, and then you contour that, and then you give it, if it's eclipse, you're going to give it a Hounsfield unit. Okay, so you're going to say it's a Hounsfield unit of whatever you think it is. And so you assign that, and then you assign the rest of the body as water. Okay? And you can do that. You can go in eclipse, you can click on the right, click on the body, you can right-click, assign CT density, and you assign the body as water. Okay? And then it doesn't use the CT pixels. It doesn't use the grayscales. Okay? So it uses whatever you've assigned to it. Because if you assign the whole thing to body, it's the assignment that you've given supersedes all the Hounsfield units. Okay, so if you assign the whole body, so every pixel in there is now water, and then the actual metal parts has been assigned to whatever Hounsfield unit. So then there's really only 2 Hounsfield units the algorithm is going to consider. Okay, and then anytime you draw a structure, by the way, the default is water. The default density for that structure is water. And then, hopefully that's a little more accurate than considering all the streaked artifacts and using pixel by pixel data with those streaked artifacts. Okay.